there's still a group coming down the hall. Well, I wanted to lead this discussion period this afternoon. I've been here for over a week, and I've heard what some people are doing, and I think maybe Vi will talk. I have about 4 slides, and then Vi will say some words about what he's doing with the G equation with turbulent combustion. And Vladimir will talk about the same general idea about G equation a little bit, and maybe keep it informal.
Where is Victor? Because Victor's supposed to be here to tell us that it's all wrong.
Where's Victor?
We'll get into our time for that.
Okay.
John, I'm not here, and yeah, over there. So.
No, okay. Now,
That's what he's saying.
should we?
He's across in the same office. Is that right? Oh, he's in the. We don't know that yet.
But let me pose a few questions, and I'm hoping that Foreman and Alan and all the rest of the group will, because there's some questions I've always had, and I really think that, you know, as we're doing measurements in turbulent combustion, we want to know, does all of this G equation theory apply? And I'm very optimistic because, you know, we've talked about other approaches, the flame surface density, or more of a statistical approach. The G equation, as Foreman pointed out, includes lots of good things that we see in the experiments. You know, some of the other approaches don't have any of this. We see flame wrinkling, we see Darius-Landau instabilities in turbulent flames, fully turbulent flames. As was pointed out, we see pocket formation and cusps. We see Huygens principle. And many turbulence models don't have these things. So even though there are some disadvantages, the G equation, I think, has a long and bright future ahead of it. Heinz Pitch has been doing really great work, as we know, applying this to turbulent subgrid models. One thing I've noticed is that he ignores the Sivashinsky integral. And, you know, I remember reading your original papers, and including the ones with Bill Ashurst, and I thought it was really, really clever. I used it in my classes even to explain how distributing sources on the surface can do things that we really see. But now, from what I understand, Heinz is just ignoring that. And so he's, I guess, assuming that the velocity field that's prescribed here is given from some resolved scale solution, and that it exists on both sides of the flame, and that it's the same on both sides of the flame in a sense. He doesn't force it to change due to the flame front. At least that's my understanding. Now,
just in Foreman's first equation, you don't have this last term.
well, but I think, well, that's sort of the question I have.
So the question is, this equation, is this for constant density, and then the last term is just for the density correction? If that's the case, then in today's G equation, you have the density, it's not constant density.
Okay, I mean, that's sort of my question, and I don't know the answer, but we do see huge density changes, and it does affect the wrinkling. And if it can be included, that'd be nice. If it can't, then we won't, you know.
There's an implication in the way you presented this. I don't know if this is intended, because you presented the G equation with modeling in effect, which means in essence that some of these things really might have overbars, certain averages. This is one particular model. There are various ways that different people use the G equation in modeling, and so there's not sort of just one answer to the issue. In other words, you've got to talk about, what are people doing? I think the question was, what are the various things that people can be doing, are doing or can be doing with the G equation, and what do we think of those different things?
As long as we understand, I think there was some discussion at one of the symposia about Heinz's work, and as long as he explains to us what he's doing and what he isn't doing, but actually this equation I took right out of Heinz's paper, not your paper. And so,
Yeah,
Yeah, but that's not an equation for the G that I started out with.
Yeah.
Because the G I started out with doesn't have the ST as a
Subgrid.
subgrid, and it
Yeah.
doesn't have the I, the Shudzinski integral term. And
Well-
so you have to do something, so that G is a different G, it's a G bar, like you said.
Yeah.
But now, as we get to looking at experiments in real life, my own, there's a quote I've got here from your paper, Foreman, that the heat release does affect the
Yes.
wrinkling in some way. And
Yes.
I think we just want to keep in mind as we proceed, is that a research area that we have to include in turbulent models, or no? That's just, Heinz shows lots of good wrinkling, and he doesn't have that. Let me just make another point here. The thing I really like is that this G equation approach predicts a flame surface density, and we can measure that very nicely. Not exactly, because it's a 2D approximation to a 3D phenomenon, but you really get a good feeling if you can measure profiles of flame surface density, degrees of wrinkling, and brush thickness, that you're doing it right, rather than some other models that just give you the final answer of how much fuel is burned or something, and what distance does it burn in. This is more of a specific quantity that now we can measure and really assess models with.
I think the answer, I think it is important to take into account the effect of the density change, the wrinkles or whatever, density changes on the turbulence. That's important. But it's also interesting to do what Heinz is doing. So,
Yeah. But okay, well, as long as we know what's going on, I think there was some confusion at one of the symposia whether he was dealing with a constant density model of a variable density problem or not. Now, I can understand there'd be a lot of computational effort required to do a Sivashinsky integral, but maybe not over an entire flow, maybe over a localized region. And then this, let me go to the next slide. Heinz has this formula, which we've been discussing variations of this, Savalnikov and others here. But Heinz has proposed something like this, which his subgrid modeling has this turbulent diffusivity, and he argues that this formula is good at two Domkohler limits. At very large turbulent diffusivity, this term dominates over both of the other terms, and then the turbulent burning velocity, this is proportional to the velocity fluctuations times the integral scale. So you get something like Bradley's formula for turbulent burning velocity at a very large turbulent diffusivity. And then he argues that if it's small, then this term goes away and you get something he argues is also realistic.
So he considers the U prime to the 1/2 power to be his target. That's what he considers the right physics for the effective turbulent flame speed.
Well, he argues that Bradley has a formula that says the turbulent flame speed goes as U prime L over nu, Reynolds number, turbulent Reynolds number to the 1/2 power in at high turbulence levels. Now that's highly questionable, but it does fit some data. And I can't say it's wrong. I can't say it's right.
Yeah.
But
in that expression, the delta is equal to red.
that's right. And so
And
this
it's been used as a physically meaningful scale. I can't see that.
well, that is an issue. I think when he's done his whole model, he's got to prove to us that the result is independent of delta. And I'm I'm not well, I know that I've seen him write, and there's more to it than just taking the delta out of that equation. I think a delta should be in that equation.
I think
Right.
delta T, this diffusivity is also delta dependent. Because as the filter size goes to 0, these terms should also disappear. And asymptotically you go to dx in the T equation.
Well,
So I think dt is from Smolinski model, if I guess, with the delta in.
but if you change delta, you are putting, let's say, make it smaller, then you're putting more effort into your resolve scale solution, less on this, and so there is another contribution to the turbulent burning velocity, which is the resolve scale solution, and so this formula should have a delta in it because.
But this contradicts what Crystal Fulby was saying a couple of days ago. Whatever combustion model you use doesn't make a difference in this calculation.
Well,
I'll come
that's
back to that.
his opinion, yeah. I would happen to think that if you get the right physics of Huygens principle, wave propagation, pocket formation, you're much better than if you don't. But that's my opinion.
Yeah, and if you have the right physics, you're better than if you don't have the right physics. I agree with that.
You would think so, but
You're saying it doesn't matter what subgroup model.
Yes.
Well, that would be true if at the result, but that ties in with the idea that the overall burning rate is large scale entrainment limited, as long as your entrainment velocity in effect is larger than your propagation velocity, you're probably okay.
That was not my statement, that was a statement made by another person.
Anyway, I'm just saying I like that statement. I can understand the basis for it.
I think Christer means that in terms of statistics, it's not the real physics. If you look at your time average, everything, then it's not very sensitive to different surface models. That's what they claim.
For example, we can't extract physics from LES, can we?
What?
This is only valid for some cases where the burning is very sufficient. Very good.
Is it possible? I don't know, I'm just posing a question. Is it possible to extract some physics from LES calculations?
What
This
do
is
you think
compared
we're
to
doing?
experiment and interpret it.
That's again statistical comparison, right? When we compare the
That's
experiments.
how we learn, that's how we do experiments.
So what your LES calculation is going to depend on what you throw in the subgrid scale level.
It may or may not be sensitive. If it's sensitive to uncertain physics, then you worry. If it's insensitive, well, that's good.
well, I mean, in the back of my mind, I'm always thinking premix flames are waves. If you don't have wave physics in the model of a premix flame, then why don't you just take a stock market predictor and put it into your model? You know, I mean, why don't you take some model of something else and put it in? Somehow the G equation has the really nice property that you have waves, and they propagate, they form cusps and pockets. And, so, we can talk about what's the way of the future. There may be other ways of the future. Maybe it's not exactly the G equation, but I think it looks awfully attractive. And this, I guess, I have one more slide, but the point is that flame surface density is really pretty nice because you can tell what the probability of finding a flame is, and you can see where the end of the flame. This is a premix Bunsen flame. It looks like this, and I had a student from Moscow who did some nice experiments, and then John Bell did a great computation, and this is with DNS, and the primary metric we used was the flame surface density. And so I think this is kind of the way of the future too. If models can predict a quantity like that, that will be a useful thing. Now, they even computed what's the difference, you can't read this, but a two-dimensional flame surface density and a three-dimensional surface density. Because they can actually take the surface area per unit volume and compute the true surface density. And then they could take the perimeter per unit area, which means they just take a slice of their computation. And they showed about a 20% difference. And this happens to be what we can measure. And we can't measure the 3D profile, but the point is that, the typical height of the flame and the region where the surface density was started and sort of reached this peak here was in reasonable agreement with their computations.
Well, that looks like a big difference between experiment and computation.
Well, it does, except it's really this point right here that we were looking at.
Well, okay, you're looking at the plate that it agrees, but...
That's the leading edge of the brush, right? So
But
their
what
brush...
about- What about where it disagrees? I mean, you ignore that, or...
The what?
I mean, all that stuff up on top in the computation is not present in the experiment, right?
Well, it says that there's a probability of finding a flame up here. We didn't see it. We only saw it down
So there's
here.
something wrong with the model, with the computation, right? In that respect?
Could be. It could be. I mean, it could be.
It's the DNS.
Well, it's DNS. No. It isn't perfect, even though it's DNS. It did have full chemistry.
Is
Not
that
full.
perfect?
Pretty full chemistry. It had it claimed to resolve the Kolmogorov scale, but with a moving adaptive filter method, you know. So they had something that zoomed in when it needed to be, and
How much chemistry do they have?
oh, you know, I have to look it up, but it was about 15 species, so it was.
Or it's-
And that's a computation that
This
believe is actually doable, huh?
Well, now this Reynolds number is not super high either. This is, it's turbulent, but it's not super.
It's not DNS if it's AMR.
You think so?
I know so.
Why?
Well, because where you have a variable space grid, you're filtering out a lot of the waves as you come in different parts of the material. A DNS means that certainly the grid has to be pretty much fixed and not move in the whole calculation. You keep moving grids around, or even just a variably spaced grid. Imagine a fine grid here, a big grid here, a fine grid here. As you transmit waves through that region, you lose information through the region of big grid.
That's a good point.
So I wouldn't call that a DNS.
This flow is an incompressible flow.
This one is an incompressible.
This is-
Low Mach number.
Low
Low
Mach.
Okay,
Low
so,
Mach number.
the low Mach number still has waves in it that are taking
Well, that may be the answer to Foreman's question why it wasn't perfect agreement.
Well, but it's going the wrong way, you know, because Elaine is saying that you lose information, but it looks like in the DNS you got information that it's not there in the experiment.
And who knows if the chemistry is right? I mean, it could be sensitive to some fifth reactions, chemical reaction. I mean,
The metric that we used, which worked, and maybe that's why we used it, was, you know, the turbulent burning velocity is you have to determine where the flame is propagating, and we generally use the leading edge of the flame as the metric. Now, if you use the back edge of the flame, you get the wrong number here.
And did that have consistent boundary conditions? Did you have a confined flame, or what kind of?
It was unconfined, but
So who knows what's going on in the far field? I mean, especially you're talking about the tail, you know, far
a
downstream.
better experiment. We did the experiment and sent them the data.
Yeah.
And they did. A better experiment would have been probably to have confined walls at a large distance, so they could put well-defined boundary conditions at certain spots. Don't you think?
Yeah, because if you're in open flame, then you're generating a whole recirculation in your entire laboratory. I mean,
Well,
it's, you know, so you know.
And if they have all those species there too, and they have filtered out all the acoustic waves, they could be missing stuff. So there's a lot out there.
It's hard to
surface if you got
Yeah.
detailed chemistry.
It's hard for DNS to capture the far field when it's simulating an open system because it doesn't have the analog of the far field boundary conditions.
Okay, well,
And doesn't have the acoustic waves.
the leading edge of this flame looked about right. The trailing edge doesn't.
What
So-
That's
what
good.
was the inflow conditions?
The inflow conditions,
Yeah.
we had a grid that created turbulence, about 10%
The
turbulence,
ability to
and
simulate the far field as
the
compared
mean flow was about 1 to 2 meters per second.
Yeah, but it's also very difficult to get equal in DNS and experiments, so it's also a different problem.
They had a top
Yeah.
as well.
Yeah, okay, but then get the token with the right length scales and the right intensity of all cases.
Well,
it's a good difference there.
The last thing I want to put up here before Brian starts his talk is Adam Steinberg is a student former student who's been working for me, and now he's at DLR. But he started looking at vortices in flames, and so this is the same flame that I just showed you. Here's the flame boundary. Here's the reactance, and it's actually like at an angle. But we're looking at a very small field of view, and there are some eddies, real turbulent eddies, but we're only slicing them. And I showed this to some of the audience. I wanted to just make the point, this is related to what Foreman was saying, you know, our hydrodynamic instabilities in this flow, this fully, not high Reynolds numbers, but fully turbulent flow. And we do see hydrodynamic instabilities. In this particular sequence, this is now, we're showing the eddies move through. These are measured with a high-speed laser system. The vortex pair, which we've identified, is wrinkling the flame in pretty much the manner that you've published papers on, and Don Kohler has published papers. But the vortex pair disappears, and we'll show this. As it goes through, it disappears, and a wrinkle in the flame appears. Okay, there. Now, a wrinkle has occurred. The original vorticity is gone. So this is a little bit of a violation of the G equation with constant velocity field, because the flame is destroying the vorticity. It's expanding the gas. Maybe the circulation is conserved, but the vorticity, which is the, you know, the focused rotation of the fluid elements, it's spread out so that essentially it's gone. And then after the vortex disappears, this thing continues to wrinkle and gets quite wrinkled. And so I asked Adam, you know, is that a hydrodynamic instability? Because you have no more vortex, but it's still wrinkling. And he said yes, and he showed me data that shows that it's there. And let's go to the, this is another sequence of that, of this kind of wrinkling. And okay, so what he did was he found some images. This is a movie of thousands of images. Again, after the vortex has disappeared, what does the flow of streak line patterns look like? And these are all measurements. Now I've turned it so that it looks like Foreman's picture. But this is directly, I think this is stolen right from your book, or close to it. And we see patterns in which the measured patterns look like the patterns, and you get a strain field. There's no more vorticity around, but it's strain just due to the streamline patterns. So what Adam was observing in his measurements, that early times of the flame-eddy interaction, eddies create small wrinkles, and in later times, eddies are destroyed and wrinkles are amplified by what looks to us like a Darius-Landau instability. So it's there. Now, we've had some arguments with Savelnikov and Vladimir and others. You know, if the turbulence level was to go way up, maybe the effect of this would be smaller, but we definitely see it. And I'll just show a couple
These
more
pictures here. First of all, the black line is the G equals 0 contour, right?
Yeah, that's the flame.
And there is a feedback back onto the flow from and that you obtain from the G equation.
Exactly.
So can you explain, or do you have the formula how to do it exactly? How do you exactly calculate the heating term from the G equation?
Oh no, this is not the issue. These are directly measurements.
Yeah.
Only measurements.
Or measurements.
These are only measurements. These are measured. This is the, you know, these, you imagine vortices here.
Yes.
But now we're not showing the vorticity, we're showing the streamline patterns. And Swami was showing that the flame affects the flow pattern. And so these are measurements that show that, you know, what we just heard in the last seminar does apply to turbulent flames. And so again, that's my last statement, that I think you need to put this into the models. I think it's there, I think it's real, and if you don't have it in a model, I'd be a little worried.
So you're saying Heinz did it wrong because he didn't have this effect?
Well, he has a tougher test. You have scale separation here. Assume that the thickness of the black line is roughly in the ballpark of your reaction zone thickness. Is that fair?
I can't.
Well, let me put as a question. What's the reaction zone thickness, just roughly on this?
Yeah, it's roughly the thickness of the black
Yes,
line.
so you have a very nice scale separation
We do.
between your flame thickness and your flows. Okay, and in that situation, you have the advantage of whether you use the G equation or anything else, you're going to get a very nice representation of this. If you're trying to do turbulence, yeah. Then the turbulence, the question is, are you still deeply in the flamelet regime, for example?
We are deeply in the flamelet.
In this regime, but I'm saying, in terms of what Heinz is trying to do, he doesn't have the luxury of this nice scale separation built into his physics that he can resolve. Okay, so there's got to be some compromises.
Yeah.
Okay, so then you got to, then you got to drill in and say, well, what's the best way of treating?
That's a pretty tough experiment to get that kind of detail out of
But
it.
it took the student about 5 years, and we had to invent some new diagnostics. It's a laser sheet that's pulsed at 1,100 frames a second. He has almost more data than some of the DNS people. You know, he's got.
And the seeding particles are.
They're aluminum oxide. But the experiment only works under these fairly low turbulence conditions. So maybe someday somebody will do this whole experiment under much more turbulence.
Well, I think the DNS, there's probably a tractable DNS that can address what happens when the turbulent length scales get a little closer to small scales of the flame.
Actually,
That would be a very nice DNS in the box. That would be a nice case.
When Adam Steinberg was starting, I told him, that's the problem I'd really like you to work on. But he was smarter than I am. He said, no, I don't want to do that problem. I want to do this problem. And as we went through so many problems that he was absolutely right. It's going to take some other student 8 years to do.
This is very hard for a laboratory. I mean, I think it should be a computation. Because the issue is whether it's not only a length scale separation, you also have a time scale separation here, because the residence time of the reactant in the flame zone is much less than the flow time scale.
Well, the last thing I'm going to say is I fully believe that this is not what you assess LES with. I think that you assess DNS with this. In other words, somebody does a DNS at Berkeley, let's say. We actually assess the DNS to see if they've done it right, and then after we feel like, hey, get rid of these problems that the formula was talking about. Then we say, let's use the DNS but I don't think you can even use DNS quite yet to validate LES. I don't think it's quite.
I was suggesting they're very specific. Just to study the physics of the interaction of the Kolmogorov eddies that are as small in space and time scales as your flame reaction zone times, and see whether the instabilities still survive, or whether the Kolmogorov eddies in that situation disrupt them before they can even start to grow. It's just that qualitative question, even to study with DNS, is just a kind of an abstract kind of question.
I just wanted to point out that I'm really optimistic about G equation approaches if the community can get them to work. Because
there was a paper by Ken Bray in another symposium trying to introduce the stability
he did put that in his model, and that I thought was very useful too.
Did you be able to compare?
Well, no, because we don't run models, so we aren't computational people. So if there was somebody else who wanted to, I'll let Bai take over now, and he's going to show how all this might work in true simulation.
back to the first one. So for those who do not know me, I'm Byron, working in Sweden, the south part of Sweden, Lund University. We have been using G equation in the last 10 years almost. Well, started because we read Peter's book, Peter's papers, and we say, oh, this is probably a good one, because Peters usually have a good sense. So that's where we started. And then I will tell you some of the stories later. We encountered some problems, not only in the modeling itself, but in numerics. So I want to talk some numerical issues. So hopefully you'll give me some feedback. So maybe I can also start from this, what Foreman has been talking about. This is the G equation. It can be derived from a phenomenological approach. It's a propagation equation again, you all agree. And here, if the SL is known, lambda blending velocity, if it is known, then this equation essentially can track the flame propagation, if the numerics is right. Everybody agree with me? But
in fact, the lambda barrier stability is not built in. You have to decouple. You have to couple with the.
It's implicitly built in because
of the V.
Because of the velocity here, or because this is not a constant density equation. So you do have the heat release effects which deflect the streamlines, and that is the non-modulus instability effects. So
I mean, if you impose the V, if you have an impose, if you have no feedback of the V,
you impose V. You couple this with the
you have to couple it with the
Navier-Stokes.
V depends on G.
V depends on G.
So it's not so simple. I mean.
No, it's not so simple. In fact, it's very difficult.
You know, probably you should show. You should show some cusps. Probably, you know what I mean?
Yeah.
Probably should.
You
With that equation,
you can develop.
By the time it got that far, there would be some cusp pointing to the some sharp corners.
Yeah, yeah. But this is handwriting, so it's not a simulation.
Well,
anyway.
it's an interesting. Even those might not survive all the strong turbulence. I mean, it also takes time to develop. It's not instantaneous.
Yeah.
Bifurcation.
Yeah.
So who knows if the turbulence prevents that too?
Well, there'll be some.
Yeah.
There's got to be some.
I see.
Anyway, here, this is the instantaneous one. So we use LES, left-hand speech. So the idea of LES is that now we have this larger AD room for the flame is to be simulated. And then these small AD effects, they are filtered out. The question is, now this large AD flame front is not propagating at the speed of local SL. So you need some modeling involved. So this is the issue. I think Foreman talk about this. You can do this. Essentially, it's a ratio of the surface area to this filtered area. So if you know that, then this term is closed.
I assume mean. When you say mean, you mean it's spatially filtered.
Yeah, this means spatial filtered.
Right.
Is filtering is well defined?
Yeah, filtering is well defined, but what you filtered out is an unknown, so you don't know. Because this is physics. That's physics. It's numerically filtered out. Then you have to account for that. Well, we have a lot of discussions.
You heard before that this equation actually supports waves. Can some of you elaborate more on that? I mean, is that a version also still supporting waves?
I think.
And the wave speed is SGS in this case.
I'm using the word waves where I think fronts would be the more precise description. Because waves have certain characters. It's not a computer.
Okay.
A wave is kind of an oscillating thing. A front just sort of propagates.
equation
A wave
describes
is a
motion
front.
in front, that's right.
A wave, fronts are associated with waves. A front is one characteristic of a wave, but if you have a front, that doesn't mean you have all the other characteristics.
I guess
of a
you
wave.
can have just a wave going by, a sine wave, there's not much of a front there.
Well, I mean, it's like every light waves. You have the iconal, you have the, you know, but you don't. There's not the inverse implication that a front has an underlying wave.
Right.
So,
That's good.
so somebody can have a subgrid model that reasonably well represented the bringing the loss to information, then LES could be very useful with the G equation. Otherwise, it can be very dangerous to use the G equation because suppose you have an error in the SDS, then your claim will totally wrong. Totally wrong. So that's something. So we have used the G equation to simulate many things. This is one of the things. Is a low-swirl burner designed by Rosenthal and Lund University Marcus Adinslav ordered one such rig. We did a lot of experiments in the last 4 years. It's essentially like this. We have a swirl down there, generates some kind of weak rotational flow. And then this flow at the edge of this is a higher velocity, in the center have a lower velocity. So the idea is that this velocity is so low that you can have a stable flame. It's not due to the vortex breakdown of the swirling flow, but due to a different blockage here. You have a low speed profile and a high speed profile, so you can stabilize it. So Marcus experimental people said, okay, well, can you use the G equation to simulate this front? It's very complex front, 3-dimensional. So that's what we did. So they did the measurements. This is what they found. Have this leading front. This is fuel acetylene seeded to the fuel, so you can see it. This is OH, so you see it. So the interface of this is likely the flame front. And you see some nice features here. You have holes. This is probably due to the dilution. This is open flame. Dilution of air into the flame front. It's very complex. And we heard that T equation is not valid for cases with a flame front, but we try to use it anyway.
You mean with the holes?
Huh?
Not valid for
not valid when you have a hole.
holes, right?
Yeah, when you have a hole. But I have animation. Should animate. This is what we get. T equation look like a real flame or not?
What you're showing is actually the G quantity itself.
Yeah. No, this is temperature. Coupled Navier-Stokes with a heat release with density change and G equation.
Well,
Okay, what is the quantity we see here?
Temperature.
Temperature, yeah, fine.
if you artificially change your chemistry to prevent the quenching, the amount of quenching you have in the experiment on the left is probably not sufficient to really change the overall dynamics. So if you really just want to see the overall dynamics, you could simply tweak the chemistry to prevent the quench. You're going to see almost the same dynamics anyway. Which is what happened.
You mean the quenching here? Oh.
What I'm saying is, even if you ran it, you just change your chemistry so you won't quench under these flow conditions, right?
Yeah.
It's not going to change your dynamics significantly. So you would expect. So you can still get the overall structure of a flame that's quenching just by, in your numerics, artificially turn off the quench. You're not going to get the holes, but you could run two chemistries simultaneously. One for the dynamics with the G equation that's artificially prevented from quenching, and separately, just sort of riding along as a slave, you could run the full chemistry and see the holes.
what you do is an even cheaper way.
Oh, okay.
So what we have is, here we have the flame hole. Okay. So this, we know that this flame hole is due to air dilution. The mixture is so lean, so you do not have a flame. So we use equivalence ratio as an indicator. If it's below the flammability limit, then we simply say flame speed here is 0. Flame speed here is 0. And the rest, we use the flame speed as a functionally local equilibrium ratio. In that way, we get this picture. And of course, you have to solve the fuel equation on top of the G equation. I think the good thing about the G equation is that it finds the flame front, propagating flame front. We don't have to rely on the average, the source terms of the reaction rate to find the flame front. So we use this information. Suppose we know that from the G equation we know the flame front, and we know that our LES will not resolve the reaction zones because it's a flame-like regime. So we add a fuel equation. In the fuel equation, we have a source term that is very large, but is very small before, in front of the flame, and very large after the flame. So it finishes within 1 grid, you finish the fuel. But then the fuel cannot be finished in these holes. So in this way, it's a model.
Interestingly, so these holes you're claiming, the holes you can see are the holes that are resolved at the mesh scale. I mean, it doesn't, yeah. So,
yeah.
Right. Okay. So
this is quite big.
Right. So that also involves some coarse graining of the underlying field. So that's kind of the modeling errors. You know, that you don't really know in detail whether in fact it's just a lot of little holes and you just kind of coarse graining them into a big one.
Yes. Because we cannot have very small holes. The grid does not support it. Right.
It would be nice if you sometime you plotted the G equals 0 contour, and then I mean G equals 0. That's, I assume, the line between the yellow and the black, right?
Yeah.
And
here we have another separated one.
But maybe you could even put you could just stop the contour where you knew
we have that information.
where the reaction is essentially. You do know that, right?
We have that information.
Yeah, that would be really interesting, because then you could compare the number of holes and the general hole structure in the simulation to the holes. That would really be interesting.
That's a good idea.
You didn't tell us what you did to the subgrid.
Yeah. That's the main point.
You mean as the S term?
Yeah. Yeah.
That's a good question. We use rather simple model. SL. In many cases, I think in this case we have a model that essentially very similar to Hans Pietsch used. You know, in this Peter's book, he had for runs, he had this model that valid for both flamelet and thin reaction zone.
Yes.
This is exactly the LES version we use.
I see.
LES version of that one.
I see.
We have this is some of these results were published in symposium 3 years ago, 4 years ago. There we have this model.
The red is burnt, I guess, right?
The red is high temperature.
Yeah. How do you get temperature variation with a G
because
equation?
of dilution. Basically, it's a dilution.
Oh, I see.
If you have a pure premix flame, you see red, blue, red, black. Yeah, that's
Your subgrid model does not take into account the wrinkling?
well, it's included, you know, small scales. That's what it does. If you do not include wrinkling, this will be SL.
Yeah.
I mean, here I have a bunch of terms.
Okay.
Delta has this is dt. That's why I know dt. dt usually is a function of subgrid scale velocity times the length of the filter size. So I have these. I think Heinz-Pitschi's model is very similar to what Peters was talking about for the runs. So you asymptotically approach to the right limit. So now interesting. This is what we get from a thickened flame, Christopher. We worked a lot together because he's also interested in this flame. So he used the thickened flame-like model. It's not exactly the thickened flame. What he used was using detailed chemistry and just couple it to the running, the detailed chemistry. Usually the grid is so close, so reaction cannot finish within one grid. It finishes in 5, 6, 10 grids. And that way the flame is thickened over.
Does the thickened flame have a G equation or no G equation?
No G equation. This is the reaction rate coupled with the chemical species, 5 species, global reaction. So I think two-step chemistry.
It's an LES. Christopher, this does LES.
It's a LES.
Yeah.
LES because you don't resolve it, so it kind of will thicken. To me, it's like a thickened flame.
Okay.
So the thickened flame is like this. This is instantaneous, so you don't see these fine structures as we see in the experiment. So that I think that's the that's what this model has been given away. You have to sacrifice some of the details. And this is what G equation gives. We have seen this animation. So the G equation compare with it. So G equation gives you very sharp interface because I think this is more physical because within LES we do not resolve the reaction zone. So essentially we have a density change within one grid, very sharp. Of course you need very robust numerical methods. Ghost cell methods, for example, a guy in Stanford, I think his name is Fetki. He did a lot of nice things. So he had this ghost cell methods. I see that Heinz-Pitschi also implemented this method. So this is very essential. The Lambda W's instability is to be resolved, to be taken into account only if you have a thin flame. If your flame is very thick, then your streamlines do not deflect in that physical way. Then you do not have this phenomenon. So G equation has that feature.
You say the G. I'm trying to be careful about distinguishing, a formulation from the modeling that goes underneath it. The way I would express the thought that you just stated is that if you're doing the thickened flame, you're using an artificial eddy diffusivity, and therefore you have some effective, and you also have an effective reaction. Yet the diffusion reaction have to interact in such a way as they'll produce some propagating front.
Yeah.
Whereas in the G equation, you already have the surface, you just have to model it as sub L. And for reasons that I guess you have to really drill to the details to establish, the SL modeling is more effective or less subject to the numerical smearing than if you're doing the diffusion reaction.
That's not exactly what I mean.
Okay.
What I mean is that, what you said will be effective, will be influential on the flame width or how big the flame is.
Yeah.
How fast or how high this liquid.
Yeah.
What I mean is that across the flame, when you have the G model of this type, you have density change, follows, you have sudden density change, rather than a smeared, smooth, thicker flame. So in this way, you can have this wrinkling rather sharp to me, due to.
But the equation you wrote on the blackboard for the subgrid turbulent burning velocity, that should have a thickened flame component to it, right? I mean, that's what Pitch has argued, that
that for large turbulence intensities, the turbulent diffusivity starts to appear in that. And so it seems to me that you're kind of getting the best of both worlds, because you're using the G equation and you're getting a nice wave shape, and then you're putting on top of that wave a speed that depends on eddies getting inside the wave, which whatever formula you use. You know what I'm saying? I would think that a thickened flame would be a G equation with the proper burning velocity. That would be, to me, that would be, I think that would be really nice.
I think to me this DT doesn't necessarily mean diffusion or thickening the flame. This is together with, when taking into account the wrinkling effects that you dropped, that has to be the diffusion. G diffusion is very hard to understand. Yeah.
Well,
it's a wrinkling. Yeah?
The turbulent diffusivity acts to increase the overall consumption burning rate through entrainment.
Yeah.
Okay, and in a diffusion reaction representation, you have no choice but to have the effect of that represented as thickening the flame. In the G equation method, the algorithm doesn't force you to create thick fronts in order to capture that effect in a coarse-grained simulation.
I guess maybe the word thickened flame is something we aren't agreeing on. I mean, I think when you say thickened flame, you mean the brush, the flame brush is thick.
Reaction zone thicker.
Reaction zone.
Reaction zone thicker.
With the thickened flame, what he meant is the point soap model. Is that right? Thickened flame.
Well, they explicitly call it the thickened flame,
Yeah.
but what I'm talking about is a Furby's implementation using a bit different kinetics. Okay, so that's what we have practiced. That's not what I want to show mainly, but what I want to show is numerical solution of this equation is quite difficult. I can give also some background information. I think many of you knows it. This is the G equation. Well, this is phi. It doesn't matter. G, F contains the velocity and also the propagation in this form. And this N is the normal unit vector pointing to the unburned side, defined in this way. So now the first question is, how do we solve this equation? Or maybe the first question is this equation valid everywhere? Okay, Coleman said it's valid everywhere, but it's only meaningful at the flame front, physical meaning. So you solve this equation. First of all, this interface has a big density change. So normally your schemes with numerical diffusion to stabilize the whole thing will disturb this front. You change this front somehow. High order schemes usually have oscillations. So in the beginning of the 90s, these guys published paper in JCP. They using a trapping method. That is, you have a grease that is used to describe the flame front, and this grease moves together with the flame front. Vladimir, we had some discussion how to do this in a Lagrangian way, and they've done that in '92. Well, this method is very hard to implement for 3D. They demonstrated, I think, in 1D and 2D. 3D is very difficult. Another issue is that you have capacitor, you have your grids initially, your grid points initially you have a uniform. Gradually, because they move at different speed, they can be clustered to one place and become very coarse in another place. So you have to add points to the coarse part and subtract points when you have a cluster. So in this way, in the moving grace, it becomes very messy. So that's why also these people, they're using a Eulerian way to solve this equation. Well, they solve, in fact, they solve the entire field for all level sets. So G equation is not only valid at the front, but everywhere. So in this way, but it's only a zero level set. This zero level set is not explicitly at any grid points. It's embedded in a non-moving Cartesian grids. For example, your G equal to 0. Usually you define your G at the corner of the cell, but your 0 G is implicitly given inside using this function. So this is the so-called embedded in the domain. But then you have a question, you have a problem. We know that physically the flame front moves by itself. It's not affected by upstream condition or implicitly, not downstream condition. So if you have this equation solved everywhere, so what boundary condition do you use at far field? So what they do is they have to have a upwind or downwind information. So if you are at the flame front, downstream of the flame front, you use kind of high order upwind. Or if you are in the upstream, you use a downwind. This way, you don't need a boundary condition. Otherwise, you start your calculation from your flame front. So good thing is you don't need the moving grids, but boundary condition is a problem. Also realize that, so soon he proposed another way. So now this time is like a modern model we use today. So what also proposed is that we don't solve this G equation everywhere. Instead, we solve this equation. Well, this is very good, is consistent with what Peterson was using. Because this one essentially gave phi a meaning distance function. Because this means the distance from a point to another point is 1. So because it's a gradient, spatial gradient is 1 absolute value.
But this equation is not consistent.
That's the point.
It's not consistent with the phi equation.
Yeah.
Because to keep this condition, you have to change the velocity field outside of the surface. So
I agree with you.
For me, it's not correct.
So we invite something very hostile to.
So you change the physics.
Yeah. Well, I come back to that. So so this equation is solved outside of a narrow band. This G equation now is only solved within a narrow band.
But even in narrow band, you change the gradients of velocity. Because the gradient of phi depends on the velocity gradients.
So, yeah, let me finish. I know we have discussed for 3 days.
So the equation is not valid in all space.
Okay. Well, anyway, Sussman and these people, they also in GCT, they propose that you solve not this stationary equation, but the unsteady equation. So your tau is a pseudo time. You converge to stationary solution, then essentially you have this term equal to 0. When stationary means this is 0, then you have essentially what in the bracket is 0. So psi and phi exactly means the physical meaning. Now your information is only propagating from the flame front to far field. To upstream you have a sign minus, to downstream you have a sign plus. So you guarantee that you go in the right way. So numerically what happens is that this is Sussman. Okay, I give a few words more. So that method is proposed, very nice, But just like Vladimir said, we probably have some problem here. But numerical problem, not physical problem. So what happens is that
physical problem also.
Physical problem.
Because we can obtain from phi equation for gradient of phi. And this equation, it's not compatible with velocity field.
I know.
Okay?
I know.
But
but the equation doesn't say anything about the velocity field, right?
But if we want to solve everywhere G equation,
yes,
we are obliged to take the velocity from where? From Navier-Stokes.
Yes. You take, you can.
No, I would like to tell you, this is a very important point, because in fact, this phi equation equals 0. Okay? I can obtain from this equation for, I compare this equation.
Yes.
And I will see to satisfy this condition, I have some container on the velocity gradient. Otherwise, this equation is not satisfied.
So it says again, is this NS, of course, in the evolution equation? Yes.
No, so, look, this equation we want to solve.
Yes.
Okay? And there are some problems, numerical, I don't discuss it. The people who want to solve add some new equation. Okay, okay? But I can obtain from the first equation, strict equation for this, for the gradient of
evolution equation.
Evolution equation,
Yeah, yeah.
strict. And I will see
And it's different from that, of course.
it's different.
Yeah.
And I will see that to satisfy this equation, I have to change the velocity field. Okay? So
Yes, right.
this is a contradiction.
Yeah, sure.
Okay? And of course, maybe it's contradiction in the position of the framelet and so on. But there are some contradiction. Maybe velocity is not continuous. I know there are some physics and there are some mathematics, and I see even from the level of mathematics there are some problems. Okay?
My understanding of this problem is something else, not exactly what you said. But let me continue this story. So when you have these two equations you want to solve, essentially the G equation gives you the flame front, which gives you the boundary condition, and then you find the distance function outside the flame front. So that's very good. But what happens because of this property? Our G is implicitly embedded in the grids. So your reinitialization function or distance function, essentially you have to change these functions during the reinitialization step. In this way, after you do this, you probably will disturb the flame. Your G is not the original G anymore. So, so this guy in 2000, they proposed something called the subcell fix. It's a very difficult word. So what they do is, in these nearest points, they find the distance. Okay, they find the distance, and then they put this distance to this point. So then you get a distance function, right? And then, because this distance is based on this implicit function, so indeed this equation gives you implicitly the same location of the level 0, level set. So that's the whole idea of subgrid fix. But the point is, it's only okay when you have a rather smooth surface. If you have a curvature, not very big curvature, a small curvature, then you change this point, it will affect that point. You change that point, it will affect this point. So basically, we have a problem that we have too many unknowns for too little equations. You cannot fix this. It's not possible to self-fix. since 2000, there have been many authors trying to look at this issue. I have many papers if you're interested. So last year, I had a student. We spent quite some time looking at different models, different methods, and try to compare them. And unfortunately, we found that none of these methods works. And we tried to send the paper to JCP. And then they said, you cannot just simply blame others. Nothing is working. No, it's working for their case, not working for your case. It doesn't mean that, it might be that your implementation is wrong. Well, which can be true, but you know, we're trying to do very careful work and compare really all the schemes based on the same problem. So this is one thing I want to show. This is a flame, not a flame. It's a propagating, self-propagating circle. There's no flow. Imagine that this surface has a different burning velocity. Some part of it is burning on this direction. Some part is burning in that direction. So as time develops, it forms this structure, very wrinkled flame, right? And then this propagation is periodic in time, so it will return to this equilibrium. Exact solution is that it becomes a circle. A bad method will return to this shape. So this is a test case where you can put all the schemes in and try. And many of the schemes are indeed good for this. Many schemes indeed perform very well. This is another case that you have two spheres that moves. Now they do not propagate. Now they are moving, like you have a connection towards each other. Good method will look like this, they merge. A bad method will look like this. During this moving of the grease, moving of the interface, something disturbs. Unfortunately, all methods we test have this, more or less you have this disturbance. For uniform grease, some of them do not have disturbance. For uniform grease. So if you have a code which unstructured, complex grease, is hopeless with this method.
But if you have say a block grid, it should be all right.
Block grid is uniform. No, I mean aspect ratio has to be small.
Yeah.
It has to be a cubic.
And if you had this happening in a problem with an AMR grid with squares, say, that move, would that work or not? Because the movement
you probably, our experiences probably wouldn't work.
How well can it maintain the curvature, aside from just oscillation? If you have a sphere, will it propagate as a sphere, or will it kind of try to develop this rhomboidal shape? Because, I mean, my experience, both with thickened flames and the G, one of the reasons once I tried looking at G, because I thought maybe that can solve the problem with the curvature on the fixed grade, just degenerates, and unless you have really high resolution, I mean a lot of resolution. But I mean, for me, it didn't really improve anything going to the G equation in terms of the stability of the curvature. Can you comment on that? Because the picture in the right upper right corner, it looks like it's starting to flatten out.
Yeah, exactly. Well, some of these authors, these are the latest papers in JCP. Their scheme is give decent preservation of the same. It's quite okay. Yeah.
One more thing. I think this is irrelevant, but I thought I'd ask it anyway. I noticed that you're solving the form of equation in non-conservative form. And sometimes if we fake it somehow and put a density in and make it look like a conservation equation, we can use this conservation equation solver to get a better solution. It doesn't always work.
Yeah, I see your
You see
point.
what you mean?
Yeah. But the later tests, they are only it's not a flow. There's no density change even. This later test is only for the subsurface scheme. So to see how you do this over not well-posed problem, how this could disturb the situation. Seems very disturbing. Well, that's our experience with G. Yeah?
Axel, are we going to eat at a certain time?
Yes.
Okay.
So that's, I mean, we have I think we're having barbecue at 5, so it's good that you brought up this issue.
Okay, that's all I have.
Okay. But is it about 5 or so?
Yeah.
Okay, so Vladimir will have time.
Maybe we come back to question. You say that you can't use this, for example, absolute value equal 1 because it's inconsistent with the velocity field. But you accept the fact that you do have the freedom to reinitialization?
No.
You don't accept reinitialization?
It's in contradiction with G equation. Once you want to solve G equation, even in small bundle, with reinitialization, you have the contradiction with this equation. It's easy to show. It's easy to show.
I mean, I agree. But do you accept that reinitialization is? So you say reinitialization is not an acceptable thing to do?
We have to use this kind of technique, but in clever manner, not like that.
Oh, well.
It's just I can't use this equation independently. I can't use it.
Not for reinitialize. You cannot use it to reinitialize directions. Is that what you're saying?
I don't know how to explain that. For me, once we tell this equation is correct, and you even know, you tell that this equation is valid everywhere. Okay?
Yeah.
It's your point.
Yeah.
Okay? Once it's we accept this point of view, all information now can be obtained from this equation, including information about the gradient. I agree. So, now, if we have one equation additional, there are some conditions on the velocity gradient.
Okay, but this is not reinitialization. You're not reinitializing, right?
Yes, I agree that what, of course, there are some distribution of points in the surface, and we have to manage these points.
Yeah.
But without, of course, after we can calculate the distance, we can do, but without perturbation of velocity fields, in this very thing.
I guess my point would be that when you're solving the G equation, definitely you need the velocity field, okay? Yeah, and you have this, but from time to time, you have the freedom to reinitialize. Now, the only restriction you have in reinitialization is that G equals 0 must remain wherever G equals 0 was. But any place away from G equals 0, you have total freedom independent of the velocity field to reinitialize however you wish.
The gradient of V on the surface is given by the equation itself.
Yes.
It's given.
Yes.
Once we know this gradient of velocity, we can find the gradient of V at the surface. I agree with that.
Yeah.
So, here we have information about velocity field in very small region of the flame. Okay? So we have these gradients. And if these gradients are known, we can find from these equations these gradients. They are fixed by velocity gradients. It's not free parameter. Okay?
Okay, let me ask you the question differently. You saw a list of publications that Bob just showed.
Yeah.
Are those publications wrong?
Well, formal. This is not correct question because
because
I guess
it's a very easy question. Yes.
No, I don't know. I'm not specialist in the calculation. But when I speak with the people who do the calculations, they have a lot of numerical problems, and I guess I pose this question: what is the reason of this numerical problem? Maybe the reason this is incompatibility with this physical constriction. I don't know. Why you ask me if I don't I don't do this calculation?
Yeah, I'm just trying to understand what your viewpoint is. I mean, either they were right or they're wrong, but you're not telling me. Okay. You're not telling me.
So, but I will speak about another thing. First, I return a little bit to the G equation. First, I will speak a little bit about instantaneous G equation. I prepare something. I will write.
You don't have it there?
No, maybe because I have not much time, so I have to speak. So I consider for simplicity the density constant. Okay? And I will consider, again for simplicity, the case when we have a
density constant. That makes things a lot easier. That's for sure. Yeah. That's what Bill took advantage of.
We have this asymptotic
Yeah.
formula.
Yeah.
Can I speak?
Yes, please. Sorry.
So I consider this asymptotics. This is a Frank-Kamenetsky Lagrange asymptotics. The structure of the flame in this case is very simple. So we have this asymptotics. The quick change of the gradient. So what we have? In fact, we have some surface with a variance variable with a c equal 1 and gradient fixed. R, it's a molecular diffusion coefficient. Okay? So, I will consider a very simple situation. I have a diabatic wall, and I have a shear flow. Y, Y. This condition is not so important because if I introduce the density, I have to do something towards the Robinson transformation, but I don't want to do that. This is just for that, okay? To understand. So now, the velocity field satisfies this condition, and now I consider the plane fade. So what we have in this case, and the steady condition, steady flame. There are no source term because I use this Frank-Kamenetsky-Zeldovich limit. Okay? So the velocity of this surface is not fixed, but is determined as a part of solution of this problem. Okay? This problem was first solved by Trimmer. 62. So now it's very simple. So for example, if x0 is the position of the flame. I integrate this equation from x0. I can integrate from low, but this is the same equation, up to infinity, all the equation. So this term drops, there are no gradients at 0 and infinity. And finally I will have this solution, this result. Is a strict result obtained in this statement of the problem. I repeat that it's a Franco-Mineski-Zelitovich limit. And we see from this equation that the velocity of the flame, is not equal to the velocity consumption, because SL, this is the velocity consumption. It's not velocity of flame propagation, it's velocity of consumption. So, of course, we don't know this term, because I have to solve the problem. But this problem can be really easily solved, because there are some solutions in analytical function. It's this kind of function. But to understand the idea as a first approximation, for example, if you consider the case k very small, we can put here the linear profile, the exponential profile, and to define the very normal result from Klimov that cell equal P0 plus K delta F. So it's a limit when K, it's a gradient of velocity, tends to 0. In general case, of course, in this case it's very small, it's negligible, but we can obtain the same result with the case when this term is not negligible. And now, using this result, what we can tell. In fact, I need this result to analyze the equation for G, for this case, for example. Why I use here SL, but not velocity of propagation of this flame. Velocity of propagation of this flame is not equal to SL. But I use here in this equation SL. It was my question to you for me.
Yeah.
Do you remember?
Yes.
So, my explanation that G equation modelize the amount of burnt gas.
Amount of
burnt gas. Consumption.
burnt gas. Oh.
Not, so it's not propagation velocity, but it's consumption velocity. I can look at this point from another side. You know that in this limit, the amount of burnt gas is determined just by the gradient of concentration, because the convection part is equal to 0. The concentration of a species equals 0. So if I put here the boundary condition, I will obtain SL. Okay? So now to obtain what amount of gas is burnt in the front, in the flame, of course I have to multiply G by elementary surface and integrate. So I will obtain SL the surface. So my point is that if we use G equation, we have to put here consumption velocity, but not propagation velocity.
Well, if you do it your way, I agree with you. But where you begin is is in the interior of the flame. That's a flame structure that you have, right?
Yes, it's like
all I was talking about using the G equation is the situation in which this term is negligible. That this goes to zero. If you, to the extent that this exists, the G equation that I was talking about is not, it does not apply.
Right.
I mean, so if the G equation is invalid, then you can't write this if this is the case.
Yes, but
this kind of thing, if you're talking about the thin reaction zone regime, then the surface is forget what you're doing. I guess it's this.
This is the.
Oh no, here it is. Here it is. Then the surface is this point here. Okay, and so this is a thin reaction zone regime. In the thin reaction zone regime, you can't use this equation. You have to have an additional diffusion.
No, this is a thin reaction. Thin reaction regime. Because
thin
reaction
yes, that's what I'm saying.
influenced by
And
the
I'm
turbulence.
saying that the G equation does not apply in this form, in the thin reaction zone regime.
Why?
This is incorrect. Why?
Why?
Because the thin reaction zone does not propagate at a fixed velocity,
But
any flame
if
velocity.
I consider in this asymptotics.
Even asymptotics, this is zero. Okay.
Oh no, it's not zero. It's
What
not
kind
zero.
of okay, this kind of asymptotics, fine. If this is not zero, this kind of asymptotics, the front does not propagate it.
But here it's not propagated. The front does propagate in this case. It's a fixed. It's a fixed in this case. Okay? But the velocity of this front is not equal as L. Is my point.
Yes, well, the velocity of the front depends on the velocity field.
Of the velocity gradient.
Yes,
This is my point.
I agree with that.
So,
Okay.
but to calculate the amount
But
of gas, I have to point here SL.
Okay.
Okay?
You can do things your way if in this particular limit, if you like, you can do it this way. But more generally, in the thin reaction zone regime, what the chemistry does is provide a gradient, a relationship between the consumption velocity and the gradient.
I agree, but this is why I would, first point, I would like to analyze some limit case, okay? Of course, the general case is more complex, I agree. But there is another point.
But so I would not do it your way. You could do it this way if you like, but I would do a balance that would relate the gradient to the amount of fuel that's
For
consumed.
laminar flame, maybe it's not important, but you will see that for turbulent flame, in the same geometry, it will be important because this term, it's a tangential fluxes.
Yes.
So, and for turbulent flame, because the thickness of the flame brush is very large,
Yeah.
it's
Okay.
not
Okay.
negligible.
Okay, but
But to understand,
all of my lecture, my entire lecture is not in this regime. I was not talking about the G equation for the thin reaction zone regime. I was talking about the G equation for the corrugated flame regime. But we can have another lecture about the G equation for the thin reaction zone regime. Which this is one approach. I agree. It's one approach.
and another point, in fact, we see now that the flame is not a position where the velocity is equal to SL. So the real flame position and the G equation, G surface position are not the same in the general case. So to use some kind of approximation for SL, which are linked with, in a general case, with a curvature, for example, of G, is not correct.
Right.
Because in general case, they are not the same surfaces.
in general, they are when you're in the corrugated flame-up regime. I was only talking about the corrugated flame.
It's not really,
Okay.
Forman, it's not to be in a position to you. Okay?
I know.
I explain what I thought about this subject.
Yes.
Just that.
Oh, that's good. But all I'm saying was what you're thinking about is the thin reaction zone regime, that's all.
Now, if you have votes, because it will be 27 this lecture.
Okay.
So, in fact, there are some problems with the equation. Derivation of mean G equation for mean position of flame. And I will explain what kind of problem we have here. So it will be a few items here, so you can look.
I think regimes are really the most fundamental thing. If we can agree that we're talking about a particular regime, then we probably will agree on what our results are. But if you're talking about one regime, and I'm talking about another regime, we're going to have a communication problem.
I thought about a regime because even in the same regime of combustion, we include here a curvature, a lot of terms additional. Why we will include these terms? If these terms are not important, as you tell, I keep just that. But we include, here included this term. Why? If these terms are not important.
That's in the modeling.
So,
yes. Okay.
But I am speaking just analytical results. Maybe it's not practical use, but it's analytical result.
Yes.
So, what does it mean derive the equation for tracking the mean turbulent flame surface in a consistent manner? So, for that, we have to find the mean velocity with which...
Are you going to tell us
No,
about
no,
this
it's just format. I speak one quarter.
Okay.
Others people spoke much more.
Okay.
If you don't like, okay, I finish. It's no problem, right? So, G equation was introduced even in the paper of Landau, 44, after it was Markstein, 51, and after Alan, by you. So this equation is very well known.
Yeah,
so,
and before that by Huygens and so on. Yes,
yes, of course,
okay.
Of course. I don't give this there.
Okay.
It's not sufficient place. I'm sorry. So I pose the problem. In fact, there are no strict derivation of the mean G equation, what I want to tell. Even if this equation is used. There are some approach which is proposed by Oberleck, okay, with patterns. And the idea is very simple. They have the characteristics of the points on the flame surface, on G surface. So, G equation is not field equation, so we can't do some averaging of this equation. So they propose to do the averaging of this equation for characteristics. And this mean characteristic to put the equation for mean G. And it will be shown just 5 minutes that it's not correct. There are some very simple counterexamples for that. Okay? So this example really very simple. So I consider the velocity field in this form. F is some stochastic function with mean value equals 0. Tau is some characteristic time, and initial position of the flame is just x equals 0. We can solve this equation strictly. It's very easy to solve in this case. This is just solution of this equation with initial conditions. So I can find the flame position in this case. I do the averaging of this equation. Now I follow the idea of what the blood will speak of. So I do the averaging of the characteristics equation. It is done, the strict result. And we see that the points which are described by mean characteristics don't belong the mean position of the flame. So there are some problems that I will speak about that 27, and I will speak about the different consumption velocity and the propagation velocity. In situation for turbulent case, for example, stagnation flame, when the flame brush is very important, and the integral, this integral is very important, it's not negligible as for laminar flame. So there are two problems, that we don't know what mean velocity to put in this equation. What mean velocity to put in this equation to calculate the propagation of the mean position of the flame. Because this example shows that there are contradictions with a usual approach like that and with a strict result. At the moment, okay. It seems it will be given 27. If you are interested by this subject.
Okay. Yes, it will be here.
It's too good. So
what did the others say? You do that.
Maybe I have one point to say about the reinitialization. I still think reinitialization is useful. Suppose we somehow knows this g equal to 0. To me, we should not try. We should try to define another function, which is d. This d function satisfied is equal to 1. And the d function, the boundary condition of the d function is based on the t equal to 0. In this way, when the g is computed, you don't use this d, but use the g. Solve the t in a narrow band.
But what does it mean there?
D. Distance function.
But how you can derive equation for this function?
No, this is distance function. It means that how far you are from the flame front.
But if the velocity field is given.
But yes, it has nothing to do with velocity. It's not interfering your, because your g, you will solve the g in narrow band.
Of course, after you can calculate this.
You can calculate this.
Yes, you can calculate.
So
but
you
it's
shouldn't try to combine these two.
It's independent of the what do you do.
I have a naive question. You said that the problems arise because of the curvature, of the local curvature of your front.
Yeah.
Is it so important to get the curvature if you only have a plane, say? Would it be so wrong to simply describe it's the mean shape of the front?
No. What I mean is not within this cell. Within two cells, you have curvature.
Okay.
If you do not allow this curvature, then you have a
I understand that. But you said that for the, I don't remember the name, the sub-cell fixing,
yeah.
You had problems, especially when your front was curved. It was not inside the...
It was not inside the
it's
grid.
larger.
It's larger.
Okay. So it's not sub-grid fixing.
It's not a sub-grid scale. It's a sub-cell fix. Oh, okay.
It's a little confusing.
It's pure numerics. It's not modeling.
But there's a funny thing that we've always found with lots of different numerical problems. This is not this one, because I haven't tried to propagate this kind of thing. But whenever we get into a situation where we're really stuck with some numerical thing, it's because the equation's wrong. Something's missing, some physics is missing. For example, if you can't solve an incompressible flow problem, sometimes you need to have a compressible problem. If you can't solve a steady state problem, it means because the dynamics are important and won't let you converge. And there's things like that over and over where the numerics are a hint that you've got to go back and understand the physics. So I think that you can't just say it's just a numerical problem. You have to look at it together. I don't know. I'm just telling you what
something
we
is
think.
missing.
I don't know. I'm just giving you experience.
I think what you say, I can tell one point. I'm not a mathematician, but you see this one thing is strange. You have the G equation. G equation is here. This term, obviously, at the G surface is not zero. This means it is the surface wrinkling, right? Surface wrinkling. But then you impose G equal to 1 immediately outside of G 0, and then you have sort of discontinuity.
Well, sometimes another thing that helps when you have real numerical problems sometimes, it helped me with the Lagrangian algorithm, which had no dissipation at all. It was to put some dissipation in. Dissipation is almost necessary in codes, some dissipation. And maybe if you get a 0-1 boundary, it shouldn't be. It should be
0-1 boundary layer.
Yeah, you need a layer. But Alex said that they use the gradient, propagating a gradient instead of a discontinuity, and he still couldn't get the spherical flames to behave properly. Although I seem to remember we kind of did in 2D many years ago, but I'm not sure that it's applicable here.
Are you talking about level 7 method?
I've never used that. We've done other kind of gradient propagation methods.
Oh, okay.
But it's the same. The idea is to solve the equation, and I'm just saying that sometimes there's problems with an equation and you can't solve it.
I think the G equation does not support this discontinuity. The G function is smooth. G function is smooth.
Can you treat it like a shock somehow with a kind of
density,
a max-min type thing on a?
If we plot the density as a function of G, density is like this. G equal to 0 here. And then it's like, but the G function itself is smooth as a function said. You need to have continuity.
Yeah.
In the first derivative.
Can you treat it like a shock? Like use a shock capturing algorithm? That's what
Density?
you're using, isn't it?
Yeah.
You're using a Wiener type thing.
We use, not for the G equation. G equation is not solved like a shock.
But if you do, you may be able to solve that 0-1 issue. If you approach it like a continuity equation and solve it like, you know, like a, make it conservative and solve it like a continuity equation. That's how we do shocks.
Okay. Yeah, thanks for that.
Some kind of a Riemann problem for
You don't need a Riemann problem. Use FCT.
People do the G equation conservatively. It's a very expensive algorithm, but if they need that, they do it.
It's not that expensive.
Well,
It's not that expensive compared to what I've seen here.
No, if you solve it, you're looking to solve far away from a narrow band.
Yeah.
Because
but you need 3D. That's what you need.
You need this 3D.
Because you may need 3D. Because I don't think, as I was saying, I don't think direction splitting is going to work too well. But you can try it and see. You can try X, Y, Z, Z, Y, X, add it and average it, and see maybe it'll work. I mean, there's other tricks. I don't know if there's papers on
I will ask Hans Peter. I think he must have also this problem.
Well, a lot of people have been working on these high accuracy schemes for G equation. Rupert Klein and Phil Colella. So
we have it.
Yeah. Oh, yeah, okay, so there's some good,
I don't know.
yeah, some pretty good schemes.
Yeah.
These two authors over there, they're from Aachen. I guess they
Yeah,
have
they should know.
discussion with people there. Peters.
Do we need to get out of here?
Does that mean the place is burning
It
down?
will be done after 3 minutes, I think. So.
It's
Oh, you
testing.
stopped it? Oh, good.
Mike, can I ask you one last question? You know, I sort of didn't quite get the final point of yours at the very end. At the end, if you were to say,
You treat it like a
from 1 to 10, 0, we don't know how to solve the G equation, 10, we do know how to solve the G equation. Where are we? What do we need to do for those of us who are not solving the G equation?
What I want to say is that this might be a problem. And when people using the G equation, this is one of the problems people have to pay
But do you
attention.
think we're like at 8 or 9 and we're almost there?
We can solve. We can solve.
We can?
Well,
I mean, for turbulent, I mean, talking about four turbulent subgrid models, I mean, Heinz has results that are published. I guess I'm a little
I know.
confused.
I think all this, if you're not careful, these wrinklings, they contain some of the numerical disturbance.
Do you agree that we're pretty close to solving G equations?
The problem, you can solve everything.
But it's not, maybe not right.
If you introduce something, a lot of numerical diffusion, you can solve everything.
So it's not.
So for me, it's not the question is the problem posed correctly or not?
Yeah, it's not quite posed.
That's
If
physics.
you solve that's what is not correct.
So we still have work to do to get there.
My opinion is that at the moment, if the problem is not posed, maybe I don't understand something, but
That's the,
I have
Well,
that's the problem.
Just from the discussion, I get the impression that we need a G equation for both.
It would be almost the same problem.
Okay, with that we should then thank certainly James for running this session, and of course the speakers contributed by and
Nobody is fighting, so I guess it be okay. I'm surprised Alan is still awake. It's just stamina of a bear.
I have strategies with the G equation sleep depriving myself during the trip and arranging my flights sort of my body clock. I don't get what kind of
Just wait till it catches up to you.
yes, I know. I don't do badly on these jet lag.
When you do the analysis, that function is not the G that I was told.
No, it's the function of the distance to a moon.
Well, I cannot say 10. But there is such a
And so it's not, I don't think it's a question of the difficulty of solving the equation. You can solve it.
Yeah.
Well, so it can be solved. So I
The
don't
question is how big an error is introduced. I mean, it's one thing to solve the wrong equation, but I'd be interested to know if it's not the right equation, subtract the wrong equation, determine the error term. Under certain circumstances, is the residual small if it's used carefully?
Kind of idea. Imagine you've got an in-plane equation, so it's the G position. Something this is the flame position.
Well, so distance function, I mean, it's almost not a question of the equation. It seems to have more to do with boundary conditions because